Good. So what I'm going to do, I'm going to try to give a rundown of what happened during the project. And I'm going to leave many details to the 15 minutes presentations from the formerly mentioned PhD students and postdocs, because in the end, it's their science I'm basically going to present today, and it's fair that they give you the details. But I want to give you a rundown of what was the project, how did we, how did we address the questions of the project, and where did we succeed and where did we fail. So. I think I'm basically, you know what the last interglacial is. And if you don't know, there's going to be Andrea Dutton telling you everything you wanted to know about it. But just to make a very quick reminder, former warm period, warmer than pre-industrial for sure, atmospheric temperature. I mean, Arctic and Antarctic atmospheric temperature, I mean, these are just estimates. They're a bit all over the place. I think I got this from Andrea's paper. 4.5 degrees Celsius higher than present. If you look at the global atmospheric temperature, plus 1 degree, the numbers might have changed in the last few years, but this is what I put in my proposal when I wrote it now in 2017, so a few years ago. And atmospheric CO2 was 280 from 290 to, let's say, 300 ppm. So basically, as we know, the last interglacial is an analog for future potential warming or for future warming, although it's an imperfect analog because the warmth was not created by CO2, but was created by, CO2 increased, but was created by orbital forcing. But it's probably one of the best periods to investigate questions such as these three big ones, which these are declined towards the future, but they can be declined towards the past. So how much did sea level rise in the last interglacial? And so how much will sea level rise if we look at a warmer future? How fast will sea level rise, and how fast was rising in the last interglacial? Were there oscillations in sea level? Were there pulses of fast rise? And last but not least, will we see at our doorstep in the future stronger storms than what we see today? And then it's good to ask ourselves if this happened already in the past. So can we see stronger storms in the geological record? That, a bit of an anticipation, that was the hardest question to ask and try to answer. And so this is basically where WARMCOASTS started in 2018, so a few years ago already. So I asked AI, so I did something modern. AI was not a thing back in 2018. I feel old. So I took the work packages of WARMCOASTS and I asked an AI generative image to picture somebody working on this project, and this is what I got. I mean, those two guys are, one is, I don't know why there's not a girl, because we had several collaborators and PhD students working on our project, but this is probably a bias of AI, just showing guys working in the field. But you see that there is one guy in the field and one guy on a computer, and my PhD students and postdocs could attest that a lot of time was spent in the office and not so much time was spent in the field. But these are the 5 work packages that we proposed to the European Union, and I'm gonna go through them quite just to give you an overview. So the first work package was something that we basically took from the well-established tradition of Holocene studies of compiling databases. But we realized, so we had some prototype of a database for the last interglacial. There's many people, Andrea compiled one, other people compiled databases, but the level of detail which was contained in the Holocene databases was not matched for the last interglacial. So we said, okay, let's try to do that. Little did I know that this was a huge task, because if in the Holocene you have only, for example, radiocarbon ages to take care of, and then you usually have a one-to-one relationship between one radiocarbon age and one sea level index point, In the last interglacial, you have any kind of things that can be used to give an age. You have optically stimulated luminescence, uranium, thorium, you have amino acid racemization, you have electron spin resonance, you have stratigraphy and chronostratigraphy. And so you need to create lots of fields. I think the last time I counted, the database has about 40 tables connected between them and about, I don't know, a ridiculous number of fields, like 600 or 700 fields that you could compile if you had all the information. So thanks to a group of authors, we managed to put together a special issue in Earth System Science Data. And this was a silver lining of COVID. So we started the database as COVID was starting, so nobody could go in the field. And so all of a sudden I had people, especially PhD students, who were, I would say, quite desperate of having their field seasons plural, probably ruined by COVID, reaching out to us and asking, hey, can we do something? Can we compile a database for X or Y area? And these are all the authors who worked on the database. We compiled this database with more than, I think now it's about 5,000 data points, because some people added data also afterwards. And yeah, it was actually a quite humbling experience to see so many people working on last interglacial. And the result, you have it in your bags. So I printed out, I had this crazy idea of printing out all the papers which came out from this special issue. So you are going to be able to bring it to your home and use it as a door stopper. That's basically what you can do. So this is WALIS, the World Atlas of Last Interglacial Shorelines. The co-editors with me were Deirdre Ryan, Colin Murray-Wallace, Matteo Vacchi, Alex Sims, and Andrea Dutton. You will hear from some of them today. And we had 62 authors, and everything is available, of course, open access. So you can go online and basically access it, open access, it's on GitHub. You can basically get the description of the fields, get everything, get the database, so download the entire database, download Excel spreadsheets. There's also some interface that you can basically use to explore the data set and then to select and download the data that you want. So this was huge because it was only work package 1. And I was really, ready to let it go once we finished this one, thanks to some additional funding by Pages, given to a student who was a geoinformatics student who actually took the database and created this interface where you can basically download a simplified version of the data structure and then do some analysis. Merging the index points into one sea level indicator. So this is how you would get a cloud point of sea level if you're just interested in not so complex analysis, right? So then you can also do more complex analysis on this. But we thought this is good for people who are just interested to explore the data a little bit. Work package 2 was actually, trying to get out in the field, get more precise data, get data that was actually usable for more precise sea level considerations. So at the beginning, I was planning to go only on between the south coast of South America and east coast of the United States, passive margins, so not a lot of tectonics. But then COVID started, and then we also dedicated some time to go to some places in Italy, which were sort of where things were happening, and where it was easier to travel for us rather than go, say, in the US or in Brazil or in Argentina, where at some point everything was shut down. We got data. It's published. I think you will hear from Carla Rubio Sandoval about this data that we got, and probably also some from Sebastian Ricciano, data in Argentina, beach ridges in Argentina. You will hear from Silas and Nikos about the east coast of the US, where we have some new data out. Yeah, following up to work I started in my PhD. In my PhD, Paul Arty brought me to this place, Myrtle Beach, and I remember he was indicating a point on the other side of the intercoastal waterway saying, oh, there's the last interglacial there. And then we moved on because we were working on the Pliocene shorelines. And then this stuck in my mind until we were able to go back and redo this and do this on the east coast of the US. And we have some new SLAGs which are going to be pretty interesting. We worked on defining a little bit better the indicative range of one of the major landforms that we can find in Patagonia. Patagonia is 6,000, 7,000, 10,000 kilometers long, I think. 4,000 kilometers long, and all the Patagonia coast is interrupted or is characterized by beach ridges, and nobody had worked on a precise classification of where a beach ridge is compared to sea level. I'm not saying we have the final answer, but at least we have something to quantify it a little bit better. We had the luck, as I was saying, during COVID, we were basically stuck in Italy. But luckily, there's some great people working in Italy and great sites. And this is when our colleague Marta Pappalardo was inviting us to join a project that they were doing between the Italian and French border, where there are caves, which, funnily enough, some of them are owned by the Prince of Monaco. And in fact, one is called the Prince of Monaco Cave. We could actually add up and team up with them in a difficult moment. And I think this is again a silver lining. You just start thinking about what you could do together, and we put our expertise together also with other excellent geomorphologists such as Marta Pappalardo, but also geoarchaeologists and geologists to work together in their project and also take something out of for our work. And this is something that was recently published. Work package 3 was in my grand scheme of ideas. When we started the project, I would say, okay, once I get the database, I do a global inversion. So I'm correcting everything for GIA, for glacial isostatic adjustment. We correct everything for topography, and we're going to have the answer to all of this. These are the dreams of grandeur. I'm going to publish that in Science. I'm going to become famous. These are the dreams of grandeur when you write a project, right? But then thinking about things, and thankfully, thanks to Blake Dyer for putting this all together, Blake was the person saying, okay, let's start small, okay? Let's have a look at what we have already from the Bahamas. This is data which was already collected, and Blake was Blake, Jackie Osterman, myself, and other people. We put together what we had, and Blake with his Bayesian skills, on top of his geology skills, put together this paper, which is the Dyer et al. 2021, where we started to put forward the idea that basically sea level in the last interglacial was maybe lower than present. I know Andrea might have a different some different things to say, but it's good. So we're gonna discuss. And at the same time, with Dan Guilford, we published this paper where we played a what if experiment, which was what if we knew what Antarctica was doing in the last interglacial. So if the last interglacial Antarctica ice sheet was giving meltwater for more than 6 meters, what would happen towards 2150? And if the Antarctica ice sheet was giving less than 3.5 meters, what would happen to the future projections? And these are the two future projections, including the marine ice cliff instability, etc. So this is something where we take what we know from the past and we try to project it to the future. This is an emulator. It's the result of a physical model and then an emulator. So there's some math in it, but I think it was an interesting thought experiment to play. And then Guilford was part of it. Another thing we did, I mean, again, my dream of grandeur was that we would do this all around the world, but then we would just concentrate it on some areas, and this came out from what we started to think with Tamara Pico and Jerry Mitrovica and other colleagues. We started to think, what about the weight of the reefs? Can this cause a isostatic rebound? So Tamara does the first calculations on that. I remember those moments where it was exciting. She sends me the calculations, and she was telling me, look, we have like a meter of effect on a big coral reef such as the Great Barrier Reef that you see up there. You have reef isostasy, GIA, dynamic topography, and the total signal. But then she reruns more accurate calculations, so a denser grid, and we realize that the effect is much smaller. So still important. So we have, say, 0.2, 20 centimeters, plus or minus 20 centimeters of movement caused by this reef isostatic adjustment. But it turns out one of the major players that we know of in places like the Great Barrier Reef is the disequilibrium created by dynamic topography. So you have last interglacial shorelines above sea level on one side towards landwards, let's say, and lower ones on the other side because of mostly dynamic topography. So that's something also we thought about. With Jackie Osterman, this is still work package 3. With Jackie Osterman, we tried to get at the question: how do we improve dynamic topography predictions? How do we manage to make them better? Because we know, yes, they work. We can do a prediction for the last interglacial, but it's a bit all over the place. And the answer of Jackie was, we need to go back in time. We can't do the same. We cannot tune a model for the last interglacial, but we have to go back in time. And so what we did with Jackie, we went back to the Pliocene. I was kind of hoping I would get rid of the Pliocene in my career after I finished my postdoc with Mo, because it's too old, it's difficult to work on it, and it's a very hard question, so I was more for simpler questions. But it haunted me again, and so we did a couple of papers with Andrew Holliday to try and understand a bit better by tuning with different data, dynamic topography over longer time scales, and then to apply them to shorter time scales. I don't want to steal too much time, but we are on time. Then we moved on to another question, which we will hear a lot in this today and in the next few days, which was, can we say something about sea level oscillations? So I think a few of us have been haunted by this question for quite some time, right? And when I was writing the proposal, I thought, okay, how can I propose something different? Maybe not something working, right? But something different. So this is where the work with stratigraphic forward models come through. So we try to say, I see a stratigraphy in place somewhere around the world. Let me see if I can reproduce that stratigraphy in a model by making the sea level oscillate, or if I just don't need that, if I just need some stable sea level to create it. So the first attempt was in this place where Patrick Boyden worked in Madagascar, and we did some modeling, and we realized that we can actually get different, decent accuracies. So these are two models by Patrick, so the results of two models by Patrick, very simple. So one is with a flat sea level curve, and the other one is with a stepped sea level curve. This is a synthetic experiment. But what he could do was basically, reproducing what we see in the field. And funnily enough, if you insert a strong pulse of sea level, the models basically lose the reef, which is something, that we observe a reef there, so we would say that we observe a reef above sea level, so we would say that that's not accurate. Instead, if you give time to the model to have basically a slow growth of the reef, then you can grow a reef and a reef crest at about 3-4 meters above present. And this turns into, I mean, this is not part of the project, but I put it up here because it's actually interesting that we do not see any, I mean, our models would argue for no sea level oscillation in the last interglacial. And this is a recent paper by Roger Krell and Jackie Osterman, where it would show where you have, let's say, the possibility to see intra-last interglacial sea level oscillations. And in that site in Madagascar, yes, you might see some minor sea level oscillations, but you would not expect a major sea level oscillations. This is done by basically separating, sorry Roger, I'm gonna summarize it in 3 words, separating the contribution of Antarctica and Greenland and calculating the glacial isostatic adjustment on top of it. Was I accurate enough? Okay, maybe we'll hear something better from you in the next few days. So basically, you know, we have all these things to think about, and it's actually quite interesting. And this is where Denovan comes on. I don't want to scoop his talk, but basically he started to do a lot of models, 50,000 I think models with different scenarios of sea level in an idealized world, and he would observe that the only geostatic explanation for a backstep fossil coral reef, as in the Yucatan Peninsula, for example, is sort of a bit of an oscillation of sea level. There are other caveats, which I'm sure Dana will go through, but if you go to the Yucatan Peninsula down there, it's one of the sites where Roger would say, yes, we see a sea level oscillation from the GIA, and separating the components. So there is something there. I don't have an answer, but there is something there. So something there. Other works we did was trying to get a sense of some morphologies which are particular here in Italy. Double tidal notches, so tidal notches which are particularly well indentated on the top side, and then like a small other indentation. This is what Nikos Georgiou did, where he modeled the formation of a tidal notch and discarded basically only the model, he kept only the models that would match the tidal notch formation. It's published, and I don't know if Nikos is going to talk about this today, but I think he's going to talk about the project in Florida. But basically, one of the solutions, not the only one solution, is that we can create these morphologies with a bit of an oscillating part. And again, if you look at Rogers, that's another place where you could expect some of this. I'm almost done. Work package 5, the hardest one, the one I wanted to work on more, but it's incredibly difficult to work on waves in the last interglacial, because preserving, to find preserved, accurate indicators for waves during a warmer period, I think it's actually very hard. You find them, but you don't know if it's if they've been deposited by tsunamis or by stronger storms or by storms which are pretty much the same as today. First thing we did was a modeling experiment where we would force a surge model, a global surge model with wind data at 124,000 years. So this is the CMIP experiment, and we just used this wind data to calculate the extremes and propagated the extremes in the world. And the funniest thing that I get out of these models is that they have wind engraved in them. So what I did at some point, I was starting to look at different locations, and we have, for example, this is an example from the Cape Verde Islands, where we have on the top panel the mean and the top 10% wind in the present interglacial simulation, and the mean wind and the top 10% wind in the last interglacial. If you look at these two panels, they basically tell you that the strong storms were actually pretty similar between today and the last interglacial. Well, that's too bad, because I had data in, we collected data in Cape Verde, and there is a very convincing boulder ridge, which is about 10 meters above modern sea level, and there's no way this ridge can form with modern storms. We tried to basically, we went back to historical images, to historical sources, and this ridge must form with a different sea level elevation. We have some ages for this Pleistocene limestone, and it's probably MIS 11. So it's preceding this boulder ridge. So this boulder ridge was created by waves crashing on top of an existing MIS 11 platform. So that screams MIS 5E, but I don't have the age for that. We did some modeling, some hydrodynamic modeling, and we started to see that as soon as the sea level rises to about 4 or 5 meters above present, you start to have enough energy to have run up on that ridge and to have waves basically throwing boulders around. Of course, there are also boulders, and I got to this work package because I had been working on the Bahamas boulders, and we received lots of comments and replies on that paper on the Bahamas boulders. Luckily, nobody has worked on the Cape Verde boulders, so we were the first ones together with our colleague Ricardo Ramallo, who has been working on tsunamis in those areas. So nobody will write a reply to this, I hope. Well, that's a hope, let's put it this way. But basically, we saw that as soon as you start rising sea level, also the probability to move the boulders, which is in the blue area, so the bluer this graffiti is, the higher the probability to move the boulders in this area raises up. As soon as you get to 4 or 5 meters of sea level, with respect to today, you have movements of these boulders. So this is something we put out there as a, it's a paper that describes what we have, but we set out the methodology to do that. So we go back to the historical images, we go back to every satellite imagery we have during storms to check what the run-up was at the time. We check lots of things to make sure that this ridge is not active anymore. And then we throw at it some modeling to understand a little bit better what was going on. The last thing we worked on is, with respect to the waves, is this paper, which is still in preparation, submitted soon, hopefully. Again, using wind models from this time from 127 kiloyears and 124 kiloyears. This is what you see. What you see here is the difference between 127 kiloyears winds and the present interglacial, and 124 and the present interglacial. So you see that in this area, which is the southern Caribbean, the three islands are Aruba, Curacao, and Bonaire. It looks like in the last interglacial wind was less strong than today, both 127 and 124 kiloyears. And what we observe by looking at the coral cover in the reefs, exposed to these winds, is that if you go to the upper section, so to the older one, to the younger one, the middle, which is mid-interglacial, and the lower one, which is early interglacial, you don't have much coral change. But the key is that you have coral reefs there in the last interglacial. You have a reef crest, which is very well developed. And to develop a reef crest, the ecologists told us, this is in work with the ecologists, you actually need not so much wave energy, but you need episodic strong storms, which is what happens already also today in the Caribbean. The point is, though, that in these areas today, exposed to the trade winds, there's no reef at all. So today, there is no modern reef on the windward side of Aruba, Curacao, and Bonaire. The only reefs you find are small corals, and I've been doing diving there, looking for corals, like desperately, trying to disprove this theory. The only corals, you find them at, say, 20 meters depth. They're these small brain corals, and there's nothing else there. The fossil coral reef, where this graph is coming for, 40 to 60% coverage. I mean, some sites, they have no coverage, but they are huge acroporas. And by huge, I mean as big as this, this part. So the acropora reef crest is really big. So something changed there. Again, this is one paper where we say, well, we should look into this because this is interesting, right? I think I'm done. So thank you very much. Just as a thank you, I would like to give a shout out to the ERC WARMCOASTS team, Deirdre, Carla, Denovan, Nikos, Silas, Chiro, and Mubashir. You guys are those who made it happen, really. I was privileged to work with all of you. Our field collaborators, some of them are here, Seba, Alex, Marta, and I'm probably forgetting somebody around there. But this was a hell of a ride, and thank you so much, because you really uplifted every idea we had. You made this happen. Thank you.